Here's the free response from the Kinetics Summative. This first one was all about the decomposition of hydrogen peroxide. They show the concentration versus time and the natural log of the concentration versus time, which is linear, so I know it's first order. In part B, I want to calculate the value of the constant K, which the easiest way to do that is probably just to find the slope of the linear graph. You could use different points, and if you used different points and your value of K differed a little bit, it was still totally acceptable. Technically, we get a negative slope, but the rate constants are reported as a positive, so we just take the absolute value. The units of the constant then just become the units of the linear graph. Taking the natural log of the concentration makes it unitless, so it's kind of like unitless over time, or you could say 1 over minutes. Now you could have also used that big equation with natural log and all that stuff that's kind of shown in part D. You can do that, and you could pick like any 2 points and plug in the natural log of the concentration and the time, and then like solve for K. You could totally do that. It's a little bit more work, but it does work. Part C was the half-life, which again, the easiest way is just to use that equation in the packet, 0.693 over K, and you get about 648 minutes, which you can also look on the graph and see if that makes sense. Now you got to go back to the first graph, the concentration versus time graph. And so if the initial concentration was 1, the time it takes to go down by half in like the blue dots, the time it takes to go down to like what, 0.5? Yeah, that's probably like somewhere around 600 and some minutes. That seems reasonable. Now again, you could also use this big equation in part D where you would just plug in natural log of 1, and then you could take that for your ln at time t, make it go down by half, plug in, okay, natural log of 0.5 equals opposite your constant, and you could solve for time. And again, you're solving for the time it takes for the initial concentration to go down by half, but it's probably easier just to use the equation in the packet. Now that does bring us to part D, where now you have to use that big equation. I want to determine the concentration after 1,300 minutes. So I'm going to go natural log of that unknown concentration minus natural log of the initial concentration, which is 1, or if you're using points off the second graph, the natural log of 1 is 0. So sometimes we just kind of fumbled on this one because we were using numbers off of the second graph, but like those are already natural logs. So you wouldn't have to like take the natural log of 0. It's already done for you. Minus opposite K, so whatever you got for your constant, times the time, 1,300 minutes. So you solve this algebraically the best you can. You'll end up with like natural log of the concentration equals negative 1.391. And to get rid of that natural log, we would do e to the negative 1.391. Now I end up with about 0.249, 0.25 moles per liter, but I can also look on the graph and see if this is reasonable. In green, like I would have maybe an easy point for like 1,200 minutes. And I could look at that on the graph and say, oh yeah, that's probably reasonable. Like maybe that would be around, I don't know, 0.3 or so. So if a little bit more time has passed, the concentration will be a little bit lower. Yeah, I'm looking for something a little bit less than 0.3. 0.249 sounds reasonable. The second part of this, the student did a second decomposition of hydrogen peroxide with an iodine catalyst in an acidic solution. So there's hydrogen ions in the equation, and the iodine ion will eventually be a catalyst. This time we want to get the rate law based on the data in the table. So here's where I want to find two trials where the concentration of one reactant changes, but the others stay the same. So let's say I want to study the H2O2. In red, I picked trials 2 and 3, where in trial 2 and 3, the concentration tripled, where then the iodine and the hydrogen stayed the same, and the rate went up by 9. Well, that's like 3 to the second power. It's second order. Then in green, if I want to study the iodine, I studied trials 1 and 4, where the concentration of the iodine doubled while the hydrogen peroxide and the hydrogen remained constant. And then between trials 1 and 4, the rate also doubled. So that's first order. Then to study the hydrogen, I looked at trials 2 and 1. Between 2 and 1, the hydrogen doubled, but the iodine and the hydrogen peroxide remained constant, and the rate was constant. That's your 0 order, which you could also just leave that out. In part F, then, you can pick any trial of data, sub in the data from that trial, solve for the value of K. That should be about 6.29. And then to get the units, I would just algebraically simplify this, and any of those units would have been acceptable. Some kind of like liter squared per mole squared seconds, or any version would be acceptable. Part G, is it likely to be a one-step mechanism? Probably not. There are 6 particles on the reactant side, so thinking that I could get all 6 to collide effectively, proper orientation, sufficient energy, it's probably just not likely. Not that it's impossible, but maybe just not likely to occur, or at least not to occur as a one-step mechanism. And then the last 2, if the student performed the reaction at a higher temperature, 2 reasons why the rate would increase. We want one to have something about collisions. One reason is that when the particles have more kinetic energy, they're colliding more frequently. And so if there's just a higher number of collisions, there should be a greater fraction of those collisions that are effective. 2, energy. We've got more particles with sufficient energy. It's like that temperature graph where I just made up temperatures like 20 degrees and 50 degrees. Well, at a higher temperature, there'd be more particles at or above that activation energy. And then finally in part I, they just wanted you to show how the energy would change if a catalyst were used. And we wanted to show something about the activation energy being lower. Now, if you drew this as a 2-step mechanism where you had like 2 bumps in your graph, but it had lower overall activation energy, that was also totally acceptable. The key was just that the curve I drew had to show lower activation energy, but I wanted the initial energy level of the reactants to be the same, and the final energy level of the products is also the same.